take a picture here. And for people who will stay for the last part, you can start thinking about problems. And if you want to present something, you can add that to the organizer so that you can come up with a schedule. So Kento,
okay. Yeah, thank you. So welcome back everyone for the part 2 of my lecture. So today, last time we basically studied what superalgebras are and what supersymmetry algebras are, and supersymmetry algebras were just a part of like some special class of super Lie algebras. And then we studied some Virasoro constraints, and then because matrix models appeared from those Virasoro constraints, and then we can now we can generalize in terms of supersymmetry in the name of super Virasoro constraints. And then, okay, at least we show that there's some sort of model exists that we can study. And then actually there's some papers that study those models and found out a recursive structure. We could do that process as well, but it's very computational, and then the conceptual part is already done. What you have to do is just to compute things, and finally you find a recursion. But we don't want to take that path. And then today we're gonna more like we're gonna change the approach completely. Okay, of course somewhat related, but now from completely different perspective in the name of super airy structures. And airy structures have been mentioned in Ranier's talk and probably in part 1 too, I don't know. But so I'm gonna do some sort of overview of super airy structures and how the recursion appears from that formula. I don't think you showed the quadratic airy structures, right? You didn't. Yeah, right. So I'm gonna have like kind of concrete formula so that you can actually see explicitly how the recursion appears from the partial differential constraint that Ranier wrote down. And then I move on to VOA parts and then I'm not gonna still define VOA, but I'm gonna go in between some conceptual part, but still we can skip the technical details and at least you feel like something should come out from that formalism. That is my goal. But please stop me like last time whenever you have questions, and I'm very happy to make this lecture interactive. All right, so now I don't know if section 3 or 2, but at least I see section 3 in my lecture notes. So super airy structure. Okay, so now again I have to set a bunch of notations. So V, this is a super vector space. Of dimension d0 slash d1 plus 1. Okay, so just for convention, I just put this dimension. I'm not saying if d1 should be odd or not. It's just the thing. It's just a thing. All right, and now, and I prepared. So now if vector space, you can think of some basis, and now you choose coordinates. And by the way, you can do this without choosing coordinates in the coordinate independent way, but it's much, much easier to understand if you set the coordinate. So I'm going to prepare even coordinates from T1 to TD0, and then odd coordinates which anti-commute as we studied last time. Tau 0, because it's D1 plus 1 dimensional. Tau 1, tau D0. Sorry, 1. So they are, of course, homogeneous coordinates, ozonic and or even and odd. I think you now have dictionary in your note. All right, very good. So this is what we normally do, but so we can actually come back to this description, but just for formalizing super airy structures, it's actually easier to combine everything into one letters, which I denote by x's. So now, I want to prepare xi, where now I goes from 0 to 1, d0 plus d1. So xi is either t case or tau case, with just a convention that, so now I want to use this coordinate. So whenever I say xi, it should be one of those coordinates. So it should be still homogeneous with the condition that x0 is actually tau 0. Is that clear? Is the notation clear? Should I write it down? I guess it's fine. Okay, so if I is not 0, it could be either even or odd. But if I is 0, it has to be odd one. So as we studied now, if you think about, so because they're just coordinates, you can think about the product in an obvious way. And so then this is true. But we have some sign convention, right? Okay, so now we have, and then, okay, I guess in principle I should write something like this. Right, so depending on the parity of these coordinates, could be either odd or even, and it may or may not pick up the sign. Does it make sense? And then, so this means that the parity of x0 is 1. I'm sorry, it might be a little confusing because x0 is 1, but this is the best way to formalize, I promise you. All right, so then now as Ranier did, I'm going to introduce a grading just to, this only for the purpose of super structures, but still, so now I define degree of any xi, no matter if it's odd or even. I define this to be 1. So if you forget all odd coordinates, it's going to be exactly the same grading as Ranier did. And then I'm now going to introduce a formal parameter, h bar. And degree of h bar is defined to be 2. And just a really minor comment, you might ask why the degree of h bar is 2. And there is no strong answer to that, but the kind of an okay-ish answer is that normally if you do non-refined topological strings or matrix models, the expansion parameter is 1 over n square. And this h bar is somewhat related to h 1 over n square, and that square thing is somehow related to this degree too. But I don't have anything other than, like anything deeper than that, so you can just take it as the definition too. All right, so anyway, so if I define degree of x, each coordinate to be 1 and h bar to be 2, and this implies that degree of h bar d by dx, which may or may not be even, is again 1. Okay, so far I just introduced that to grading, and everything else is the same. And now, as Rani, I think he denoted by what? H bar check. Did you have this check? Wait, you have here V? Is that what you say? And you didn't have H bar? Oh, wait, what? Which one is super spring? Oh, super, sorry, yeah. Yeah, I hear super, but somehow I was thinking sub. All right, so this is C of H bar and X I and H bar dx j. But I guess you're fine with this notation. I think it's clear. All right. And also, by the way, because we have h bar in this, in the definition of D, you actually don't have to worry about the normal ordering. Because even if you do some normal ordering, it just spits out h bar, which is already in this function. So you don't have to worry about normal ordering. So that's my definition of D. And all right, so now it's time to define a super array structure. A super array structure is a collection of differential operators. Hi in this stuff, dvh bar, for where now I is 1 to d0 plus d1, satisfying the following condition. So it's going to be pretty much similar to what Ranier wrote down. For each I, the degree 1 part is always just h bar d by dxi. Oh, you know what? I think you've already guessed it, but homogeneous of xi. Oh, okay, maybe this is fine. And this should be degree 2 or higher. Okay, so this is, of course, in D. So P must be in D as well by definition. And then we just say that this, the rest of, so this is only degree 1 part. And the P can contain anything higher than, oh, sorry, anything of degree 2 or higher. So it's exactly the same as Ranier's notation. And then for each I and j, they exist f, I, j, k in D again, such that hi k of hk, something like that. Yeah.
Because if your HI have higher degree
So are you asking why it should be homogeneous, or? Why? It's more like because I wanted to, but the meaning that homogeneous means, so suppose this was an odd coordinate, and then this pi must be odd as well. But it can have, for example, one. Oh yes, yeah, yeah. Oh, so sorry, yes, yeah, yeah, sorry, yeah. The homogeneous as in the super sense. Yeah, homogeneous not in the sense of degree here. Okay, yeah, okay, yeah. That's actually a fair question. Any other questions? Actually, if you do not have a question, that means you haven't understood what I'm writing. And no, not you. I want to give a little more moment if someone can realize what's going on. Any questions? Okay, maybe I can ask you a question. What is different from what Ranier wrote down? Any guess? Oh, by the way, yeah, of course, I have to take a sum. That was the case with Ranier too, right? Yeah, at least that's not what I'm asking. Yes, that is, but you can overcome that too, but it's more like a significant difference. Which one are you talking about? Self-commutative? Sorry. Yeah. Oh, sorry. Yeah, yeah, sure. This has to be in principle like super commutator. Yeah, that's okay. That's definitely true. Okay. Yes, that is also quite different from Ranier's case. Yes, that's definitely true. Okay, so now I can tell you the answer. So I said that I have d0, basically I have d0 plus d1 plus 1 coordinate. And here I said for each I from 1 to d0 plus d1. And then for each I, which means that from 1 to, sorry, this means that I is again 1 to d0 plus d1, same as this one. So it means that I do not have, okay. I do not need something like this. I do not have this type of operator in the definition of super-Lie structures. And this is not a typo. And this is very important. Okay, so is not, at least not necessarily in the definition of super-Lie structure. It's not here. Okay, and then at least for now you can accept this fact, and then I will explain later, like why we can still find a unique solution associated to this super-Lie structure. But yeah, is that fine? Okay. Okay, so because of, for these reasons, so now we have d0 plus d1 plus 1 variables. But we have only d0 plus d1 differential operators. And that's what I call this. So now the x0, which in this case just tau 0, is called the extra variable. And this is entirely the super feature. So and I'm going to explain later, if you have extra variable in the bosonic case, purely bosonic case, and you will not find unique solution of the Lie structure. You will still have, so there exists a solution, but the solution is not going to be unique anymore. And then I'm going to explain with a concrete example later. Sorry, what? Oh, yeah, exactly. Oh, yeah, sorry, yes. So this pi is in this D, which contains x0. So x0 does not appear in the degree 1 term, but x0 does appear in the higher degree part. Does that make sense? Yeah, right. So this can be any element in this D. Yes, yes, yeah. It can have derivative with respect to variable as well in this P, but never in this degree 1 term. Yeah. Okay. Okay, maybe just because it's important. So, okay. So this may contain x0 and also h bar dx0, but not in this degree 1 term. All right. So, but this is little. Okay, then okay. Let me first study a little more. Then we're gonna do some concrete calculation, which probably makes everything clear. All right. So now, so as Ranier said, so the definition of super-Lie structure or definition of Lie structure itself is just a collection of differential operators. Then you may ask, why do we need such definition? And then this definition is basically designed so that the partition function that Ranier mentioned yesterday exists and it's actually unique. But first, I'm going to define what the partition function is, and then basically the theorem will be there exists a unique partition function. So now I'm gonna let us we denote this power series. We consider So now we want to consider f, which is in power series in h bar and x. Okay, unless I specify, the indices always include 0. But because here I'm specifying that this does not, it does not. Okay, I can change the letters, but I'm pretty sure I'm gonna screw up on the board. So, okay, I'm gonna show. So we want to consider this f in the following form. Of the following form. Correct. It's just going to, so because this is going to be the solution of that differential system. In the form, so basically I want to have a coefficient in h bar g, maybe n factorial, and g greater than 0, n greater than 1, g n. Then, okay, more space. So I'm going to prepare power series of the following form. Okay, so G and N, they are exactly the same G and N in actually topological recursion and Ranieri's node. And each index here runs from 0 to d0 plus d1. Okay, so this power series include the extra variable. G minus, no, I guess, because I'm going to define partition function as e to the h over h bar. All right. I'm going to write down yes. Yeah, so, okay. Okay, so now I want to basically consider about this power series. So to given an area structure, given a super area structure, what did I phrase? A free energy. Okay, so so this is more like just a notation, but a free energy in G of free energy of is a free energy F is a power series satisfying the 4 conditions. F is even to, I don't remember the order. I see, for each G, each G and N, F, G, N is Z2 symmetric. So of course, some indices may be associated to even variables. Some of them could be odd variables. And depending on the indices, it may commute, or it may be symmetric, or it may be anti-symmetric. Does that make sense? So it's kind of the standard thing. All right, 3. So if they're all bosonic or even variables, this is exactly the same as what Ranieri wrote down. But now we have Z2 gradient with sign notation. And then, so the stable part, so F01 of I equals 0 for O. And 4 is satisfies the adjoint thing that Ranieri wrote down. So I'm writing the 4th condition at the very end because this one does not include the extra variable, because we do not even have HI in the definition of super structures. Okay, so if F satisfies these 4 conditions, we call it a free energy of the super structure that you started with. And then you can ask a question, does such F exist? And then you can also ask if the solution is unique or not. And then the answer is both yes. And that could be the only theorem I'm going to write down in my lectures. But that's more like abstract thing. I'm going to just state the theorem. But now we're going to move on to like concrete, so-called quadratic super airy structures. And that probably gives you a strong impression how the recursion appears. This is not good. Much better. Yeah. Correct. Oh, is that too small? It's conventional, yes. Yeah, yeah. It's just purely conventional. You can just.
You should think of F or the H's as canine and Z, not Z inputs, right? Z is it's just
Yeah. Good. Yeah, it's just conventional thing. I mean, I don't mind flipping it. But.
Flipping the sign is not trivial for TR. No, this is right. So it's not conventional.
Wait, but if you flip the sign, why is it going to be a problem? No, I don't get it. Because, okay, so that's the same as flipping the sign of H bar. Even if I flip the sign of H bar, the definition of airy structure just. Sorry, what?
If H bar is like next to your chin, you can't just flip the sign of H bar.
So it's not conventional. This is
Well, no, but if you swap the sign of H bar, wait. No, I think, okay, no, if you swap the sign of H bar here without changing the sign of H bar in HI, then is that what you are worried about? No, but I'm confused actually. No, I understand your question from a topological recursion point of view, but from this perspective, I just don't see how the statement breaks down. Okay, yeah, I guess I'm not satisfied by that answer, but I guess the audience is fine then. Okay, I'll think about it. Maybe I'm just missing some tiny sign detail or something. But all right, and then the theorem is that, and then, okay, again, so the question is, okay, so if it satisfies these 4 conditions, it's called a free energy, but then you can ask if it exists and if it's unique. And then the answer is yes. And then they exist.
So condition 1,
Condition
condition 2.
is Z2 symmetric. So in this, if I write in this way, each index is associated either even or odd coordinates. Okay, so if say I1 and I2 are both associated to odd coordinates, if you permute the indices, it should pick up the sign. Does that make sense? If you swap even, if one of them is even, one of them odd, and they have to be symmetric. It has to be symmetric. Remember the rule? Okay, I didn't write. You know, xi, xj is it's a power. So if one of them is actually bosonic, they always commute. Yeah, only when if both of them are odd, they anti-commute. No. All right, so now the theorem there is so given a super airy structure, there exists super airy structure, there exists a unique satisfying those conditions. All right? But okay, it's fine, it's a theorem, it's an abstract theorem, but now let's do more like concrete thing to actually understand these 4 conditions. Okay, so now, well, how do I phrase the definition? I don't remember. Yeah, yeah, the unique free energy. Is that fine? Unique free energy. Because free energy by definition satisfies all of those anyway. All right, but now a superarray structure is called quadratic if hi minus h bar del I. Okay, to be honest, the same thing. Hi is degree 2 or less. Oh. For each. And this means that concretely I can actually write everything. This means that each hi can be written in the following form. Of maybe half, just for conventional reason. K minus, there's a reason why I put the sign here, but that's okay. JK 0. And then AIJK, and this is what I mean by concretely quadratic superarray structure. Okay, because okay, x by definition, which I probably raised, is degree 1, so this term is degree 2. And you have h bar here, and x and d by dx, so this is again degree 2. And you have h bar here, so it's degree 4 here, but you have d by dx, so all of them. And then this term, it's constant, so it doesn't have degree, but h bar in front, so again, this term is degree 2. Okay, so this is, so basically, a superarray structure is classified by those choice of 4 types of complex numbers, A, B, C, D. Then, of course, not all ABCD satisfies the condition of superarray structure. Remember, like it has the left eye. So this satisfies the first condition of superarray structure, because degree 2 and the degree 1 term is only this derivative. So it's good. And then, of course, you have to check what is a commutative relation if it satisfies the second condition. So it gives some constraints on A, B, C, D. They are not all independent. They're mutually related, which I'm not going to write down, but that's okay. You just suppose you found, which actually exists, you can actually write down, find some explicit case. Suppose you find A, B, C, D satisfying the second condition. And now I'm going to think about what this means, for example, first of all. Okay, so now I have differential operators written in terms of A, B, C, D. I can act this differential operator on this series and then get some equations. And then once you get some equations, you expand in h bar and also coordinate xi's. That gives, in fact, the equation for this coefficient FGN. Does that make sense? Is that too fast? I guess it's fine. All right. So now I act. Here? You mean this? But are you asking if why? Yeah, right. Okay, yeah, this is just a conventional thing. Yeah, but sorry. Yes. Oh, yes. Sorry. That's a very good point. Very good question. Okay, I think I should stick to my original. So some papers have on the sub, some papers have a super, but when it has super, it doesn't mean the square or jth power of x. It's actually
when you do super topological, you don't do super.
yeah, right. Sorry, yeah. So yes, this is fine. All right, so now I act this. So basically, I compute this order by order in H bar, and also looking at each variable xi's, because this is going to be a bunch of power series in xi's as well. And after doing some calculus, you get the following equation: n plus 1 of I is, I'm literally taking this I from this I. In particular, this I does not include the extra variable. This goes from 1 to d0 plus d1, where this I is just a collection of I1 to IN, which can contain 0. Okay, and because this I is coming from here, which I think makes sense, so you can ask the other way around. So where does I come from? And I comes from, again, this is going to power series in H bar n x's. You look at each power, each the combination of x's. But again, this F series, if this power series contains the 0 variable, so extra variable appears in the expansion. Okay, and then the expansion part is encoded here, and that's why this contains 0. This, so each, then each AI, this is in 0, 1. Oh, it's B. Okay, of F, G, N. Okay, so, and one more time. Sorry, I know this has a lot of indices, and if you're not familiar with this indices notation, it could be very hard to follow, but I'm sorry, this is life. G. I of FG1. Okay, you can take notes or you can take a look at some papers, but I can explain at least the philosophy, what's going on. Okay, first of all, the left-hand side is omega gn plus 1. And you can, maybe it's a little messy if this is your first time to see this formula, but you can actually check that the right-hand side only depends on fg, comma n or lower in terms of Euler characteristics. So this equation is recursive, first of all. Yeah. If you need a prime or... Oh, yes. Oh, that's your question. Then yes. Yeah. So, yeah. So, yeah. Any other questions? Good. All right. So, but okay. So first of all, it's recursive. You can check that if you have time, like maybe 2 minutes, then you can probably check that. And also, this is written in terms of A. So A, D, B, C appears in this specific form. So you can also kind of see that the solution would be unique, right? Starting with, okay. So for example, as I said, 0, 2 and 0, 1 is 0. So the first non-trivial object you can check is 0, 3 or 1, 1. But this is, okay, so maybe it's better to write inverse. All right, so remark one, that formula, let's say star is recursive in 2G plus n. And then the first non-trivial one is when G equals 0 and then n equals 2. Yeah.
So G minus 1 plus 2. Second argument is that now?
Yes, it's J. Thank you. It's a very good question. Yes, that's a super important question. Thank you. And then because I haven't introduced the sign notation there yet, so if everything is even, you don't have to worry about it. But now it's a super system, so you may pick up a sign. And actually, you actually do have some sign here. Depends on the combination, depends basically on whether or not if this IL is associated to fermionic, odd or even indices. And I'm not going to write that because it's not going to be so important to understand the concept. Of course, computation is extremely important, but for this lecture, you can forget about it. And then this one, you also have sign, which you can find, for example, in one of my papers. But for now, just imagine some sign would appear here. And then coming back to your questions, this order is correct. If you swap JK, and you have to introduce some sign notation here. But if it's KJ, good. It just, you can actually check from this computation. Okay, thank you.
Okay, so maybe reset it, and we're doing some sort of sum here.
Sorry.
Next one is JX.
The next one? Oh, this. Yes. I'm sorry. Especially if you take notes on paper, I know it's difficult to shift. Yes. I mean, sometimes physicists use so-called Einstein convention, which we can always forget about the sum. And then I thought it's better to keep this. Sorry, what? Yeah. All right. So anyway, yeah. So the first non-trivial case is at least one of this or this case, and this gives f03 of I1, 2, and also 1 of I. And this, as you can see from here, you actually find out that the first one is just a I2, and then it's di. Okay, so the A term coming from here fixes f03, and then the D term coming from this constant part times h bar, that fixes f11. And then the rest you have to plug in, and then you get some formula. And you will actually find out that because this is recursive in 2G plus n, suppose you find a super-array structure which does not contain, quadratic super-array structure whose A term and D terms are both 0, and then all FGN are going to be 0 because it's recursive. Okay? So this implies that if A equals D equals 0, then FGN equals 0. And this, I'm going to give you non-trivial, in exercise, you will find non-trivial super-array structure in a sense that it has very complicated B and C term, but no A term, no D term, so that your FGN will be completely 0. And you will also find out that the Virasoro operators you studied in my last lecture they do not have A term or D terms. So the free energy or partition function of airy structure is going to be trivial. But we studied last time that matrix models are definitely non-trivial. Okay, and that's an exercise. Convince yourself what's going on. Why matrix models are not trivial, but airy structure is trivial. Okay. All right. So yeah. So now at least. So okay. This is okay. So now I just used only this condition and actually that conditions to get that recursive formula. And if you don't have the condition 3, as Raphael pointed out, you might have to have some weird notation here, and it turns out actually the solution is not going to be unique. Because airy structure doesn't know about 0, 1, and 0, 2, right? If you have non-0, 0, and 0, 2, the solution is not going to be unique. It still exists, the solution still exists, but it's not going to be unique because it depends on the choice of these guys. All right, so that's more like the importance of 3 and 4. And 2 is what Ranier said. So a priori, if you just look at this equation, it's no way clear if you can construct a Z2 symmetric FGN. And in fact, it is not in general if you choose random A, B, C, D. But if A, B, C, D satisfies the second condition of super structure, then solution is going to be symmetric. And that's what I mean by given a super structure, there exists a unique solution. So this is closely related to condition 2 of super structure. And then, yeah. And the uniqueness comes from this. This gives the uniqueness. Okay, so now you would ask, why do I need this condition? Right? Okay, a priori, okay, sure, it's a natural thing because we want to think about here e to the something, and we kind of want to have even thing on the exponent, so that somehow things make sense. But what is the role of this condition in the recursion? That is something you can ask, and this is very related to the existence of extra variable. With this condition, we don't need H0. We don't need the differential operator with respect to the extra variable. And then now I'm going to explain why this is related to the extra variable condition. So okay, so from this you can always find FGN of the following form. Okay, or in other words, that recursion does not fix something like this. This cannot be determined by that equation. Okay, but because I impose that f is even, f must have, so then x0, the 0 is associated to the odd variable. Because I impose that f must be even, there must be another, at least one odd variable, odd indices associated to this guy. But what you can do is, so now gn plus 2 of, say, odd indices, this can be fixed by this one, right? This can be fixed. So f is even means that this can be now phrased in terms of f such that now I can define, so this is odd index. Okay, maybe I should write this to be a little bigger, otherwise it looks like I0. Okay, so because there always exists at least a pair of odd indices, I can define f0 of some odd indices with whatever to be the minus of something you can fix from that equation. Okay, so imposing this f being even is equivalent of saying that I can always find f0 something from something else, from, in particular, the recursion formula. Is okay? Okay, the technical detail is fine, but if you can at least associate the existence of this condition with a zero variable, I'm happy. So now you can, at least to have a little better understanding of that condition, let's think that suppose x0 is actually even. I impose, so that's the correct definition is that x0 must be odd, and that's why we can have this condition to fix this one. But suppose, like let's assume wrongly that x0 is even, and then see what breaks down. Okay, maybe I shouldn't have done this. It's too late. All right, putting another way, if wrongly x0, the parity of x0 is 0, meaning that extra variable is bosonic. And then for each thing, you can basically do the same trick. From whatever the index you find, maybe you can actually find fgn of 0, blah, blah, blah. But in this case, you cannot determine something like this. There's no way to find a combination of in this form from the recursive formula, right? Because remember that the recursion always fixes something like this, where I cannot be 0. If I is 0, if you have something else in the other indices, you can do this game and fix the 0 dependence. But if all of them are 0, you cannot do this. And because it's even, if both, and also, in other words, okay, let's say 2. So this is non-zero if this is the case. Right? If it's odd, it has to be Z2 symmetric, has to be anti-invariant. That means f00 should be 0. And that's why you can still find uniquely what FGN should be. Okay, so if you assume this and you cannot fix this, so actually the solution still exists. If you follow the Ranier's proof yesterday, you can actually show that unless, except these coefficients, you can actually show the symmetry in terms of other indices, but you have infinitely many ambiguity in FGN. So the solution exists, but not unique. Okay. So extra variable, so this condition is actually to show that the solution is still unique. Any questions? It might be a little too technical, but that's probably always the case for the second talk anyway. Guess it's good? All right, so now we want to use this recursive formalism, which essentially looks like topological recursion, but now algebraic. Because there's no residue, there's no even geometric things going on. So sometimes people call ARE structure as an algebraic reformulation of topological recursion. At the end, you can get this FGN as an algebraic equation of all other smaller FGN and ABCD. And the same game appears if you think about higher order, so not just quadratic, if you put the rank to be, so degree to be R, for example, and you find a similar equation as Ranier wrote down, believe it or not. You can actually do that. All right, so now I want to find some non-trivial super structures from a so-called vertex operator algebra. And I'm going to okay, as I promised at the beginning, I'm not going to define everything in a very solid way, but still I'm going to give you some sort of conceptual part. Okay, so now section, was that 3? 4. Super structure. From super VOA. Okay, so very rough definition. Okay, I wouldn't even say definition. Like very rough concept of VOA is that so VOA comes with 4 data, some vector space, and some map, and then 2 special vectors inside this vector space. And V, this sometimes called space of states. So you can, for the moment, think of it as just infinite dimensional vector space. It has some Z2 grading and so ever, and then depends on the grading, it has to be finite and blah, blah, blah. There's some sort of technical condition exists, but at the moment, you can just think of it as some form of vector space. For example, yesterday, Ranier defined this as basically the ring of power series in infinite many variables. That's one way of realizing this vector space. And then Y is important. So Y is, it sends any vector in V. It takes any vector in V, and then it generates some operator acting on the vector space. Okay, so this is just, and then in particular, this is actually, it has to be power series in Z. So yeah, what is the best way to write? Yeah, okay. At least it gives some operators acting on the vector space. But so now you need 2 special vectors to call that this thing is vertex operator algebra. First of all, you have to send, but this is going to be actually power series in Z. So what is the best way to write in power series? Some formal variable Z. And so, and in particular, if I take this should be identity in the vector space. So this is the role of this special vector. So this is some sort of map from, and it takes any vector in this space of states, whatever that is, and it gives endomorphism. In particular, if you, so it basically means that there exists some sort of identity vector in this vector space, such that after taking a map, it gives the identity. Yeah. Sure. Yes. Yes. Vacuum set of correspondence, the states, and then yes. Yeah. All right. So then this is going to be, so this is going to be important object. This is called conformal vector. Meaning that now, suppose, so basically there must exist such vector and also state operator correspondence such that if this is going to be power series in Z and 1 over Z, strictly speaking. So each of Ln is in fact endomorphism on this V. But in particular, so this is more like even the definition of this Y of conformal vector, and then such that Ln equal plus times. So you can have many other vectors, and it may be very complicated vector space. It could be kind of simple, simple enough vector space like Ranier wrote down yesterday. But no matter how complicated this vector space is, there must exist a special vector such that if after applying this map state operator correspondence, then each coefficient or mode, or each endomorphism operator should satisfy the Virasoro algebra commutation relationship. Okay, so the existence of this conformal vector is important. Okay, now I want to consider a specific VOA called Heisenberg VOA. I should stop at 11, right? Okay. Any questions about? Okay, actually, it has to satisfy a little more conditions, but I'm actually skipping some details. Yeah. Yeah. Yes, that's what state operator correspondence means. Given an operator, you can recover. Okay, I understand you. Okay, so given an endomorphism vector, how can I find? How can I do that? Sorry, I can't remember at the moment. Sorry, what? Yeah, so yeah, you take some residue, right? Yeah, that's something I sort of remember, but. Yeah. Yeah, that's right. Yeah, thanks. If you want, so the VOA is basically mathematical way of defining a conformal field theory. That's how I normally think. Yeah. Translation operator is actually the same as this conformal. Yeah. L minus 1 is in fact translation. Sorry, what?
When does this translation operator means raising the operator on the state space? And then there's one that is very under.
No, translation operator basically means that L minus 1. Okay. Yeah, L minus 1 acting on, yeah. Sorry, yeah, because I wasn't even thinking of defining or even roughly defining VOA, but yeah, at least hopefully you get some sort of hint. Okay, but I'm going to give some sort of concrete example that hopefully gives some impression what you can do. All right, so then now I want to think about a specific vector space, which is almost the same as what Ranier wrote down. So in particular, so the Heisenberg VOA. This means that now the V, okay, first of all, Heisenberg, because, okay, some reason, let's, so now you have a bunch of, so now let's think about just kind of the formal operator satisfying this commutation relation. Okay. And then now from which I'm gonna basically define this V to be some, okay, maybe it's better to say span, okay, span. So this is generated, so the basis of this vector space is basically the same as C of B minus I1 acting on zero vector. Okay, so you can think about some sort of highest vector space, and then it's annihilated by all positive modes, including B0, and then also so my 0, and this, by the way, you can check that this is exactly the same as what Ranier wrote down. So if you think about this as power series in infinitely many variables, and if you think of this 0 as just 1, and as he defined, this Bn for n being positive is differential operators. So acting on 1 is actually going to be 0. So that's 1 represented. Yes, yeah. Oh, sorry. Maybe, okay, sorry. Maybe it's better not to mix up them. Sorry. Yeah, right. Yeah. But yeah, this is closely related to the J in Ranier's lecture. All right, so then it turns out this V can be, so now we have the state operator correspondence, right? And then it turns out you can always, so these modes are generated by only one single vector in this vector space. Now we say that this B minus 1 acting on 0. We almost define this as Z Bn. Okay, so if I know what B minus 1, 0 is, plug this inside the state operator correspondence, it spits out all of the B's here. And then as pointed out, you take a residue and blah, 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 you can also recover from this. You can also get some vectors. Okay. And this is called sometimes free boson operator. Okay, I'm just giving the working definitions. I know it might not be satisfactory for some mathematicians, but all right. So, but important, as I said, important thing is this conformal vector. How can I construct conformal vector from this combination? And it turns out the conformal vector can be written as I think half for just conventional reason. This is defined as a conformal vector. And then in fact, this means, and there's some formula to compute. So because now we have this explicitly, we have this conformal vector explicitly, and we know how this B minus 1 should be expanded in this way. And there's some formula that actually constructs L in terms of B. Okay, at least I think you can conceptualize it because we have something, because we know this, and we know what this is by this guy. So we can imagine at least that we can write Ln explicitly in terms of B's. This is possible. And then it turns out, because we know the structure more than just the definition of VOA general, you can write this as Z Ln such that Ln is in fact written as 2 of I plus j both in integer where is the normal line. Does it make sense? So at least conceptually, we have more structure than just the definition itself. This is an example VOA, but it has more structure. And from which we plug in this, and we actually know how to do this. There's a formula, basically, how to do this map. And then we can write Ln in terms of these B's. And each B satisfies this Heisenberg algebra. Okay? Questions? At least I'm happy if you understand the concept, and then calculations are always in the exercise. So, all right, so this is VOA. So now I want to think some sort of twisted representation. Sorry, what? What's C? Oh, central charge. 1. Yes, in the free boson is 1. Sorry, oh, you said C. Okay, yeah. Family as in what? You want to think about the beta deformation? Yeah, you can. Yeah, you can definitely think. But I don't want to talk about it because then that requires a lot of. It changes everything. That's basically I'm going to talk about in open problem session. No, I don't think. Well, okay, as long as you want to do free boson VOA, I think beta deformation is basically the only one. If you have only one free boson, then I think beta deformation is the only known. Okay, maybe you know some new thing, but sorry, say that again. Yeah.
No, yeah, so that's just one record. Not sure.
All right, good. All right, so now we want to move on to some sort of so-called twisted. So this is just a VOA, but now what you can do is now you want to think of some sort of representation. In particular, for example, if you represent these operators in terms of differential operators, and you get exactly the same Virasoro constraint as I wrote yesterday, the day before yesterday. But that's not going to be the same as what Ranier wrote the day before yesterday, when rank is 2. So even though we talk about Virasoro constraints, but the representation is completely different. And the difference is actually going to be really important. And then now I want to say some conceptual part of where the difference appears. All right, so now to think about twisted module, you have to think some twisted module. To think about twisted module of this VOA structure that I raised, you have to think about some sort of automorphism acting on the vector space. In particular, so I'm going to talk about a specific twisted module associated to this Heisenberg algebra. So let's think about, just out of blue, an automorphism. In particular, this is involution. Is it actually? Yes. Of whose action is defined by. So again, so this V is now Heisenberg VOA. So it's spanned by these states or vectors. And then I want to act in particular this B minus I1 to 0. This will be mapped to sign of sum of all I L of okay. And this automorphism is in fact different from Ranier wrote down the day before yesterday, but the Virasoro constraint is going to be equivalent. Okay. And then, so the state operator correspondence, this is always power series in Z. What twisted module does is it allows to make it fractional power series in Z. And that's more like why we wanted to think about these twisted modules. So by definition, VOA has to be power series. But for some reason, we want to think about some fractional power series just to make it a little more generalized. And then one way of doing it is to think about, so basically we allow the module to be some fractional power series. But so basically we want to think of a map from power series definition to some fractional power computational things. And then, so this means that, but it's important that sigma fixes okay, the 0 vector, identity vector, and conformal vector, which is half of B minus 1 0, are invariant under sigma. But this so-called free boson operator, if you just look at this formula, this in fact is not. This picks up a sign. If you act sigma. Okay? And then twisted module means, or at least in practice, how it works is that if the vector is invariant under the automorphism you think of, you still write it as power series after sending from the VOA to some module. If it picks up the sign, or in general, it actually picks up some roots of unity, for example. But in this case, just a sign because it's just automorphism. Sorry, of order 2. In this case, you allow whatever that picks up a sign to be power series in Z half. Okay, so that's like the working definition of this. In practice, how it works with twist module. In particular, I can probably just give you the concrete formula of 0 of. So now, okay, this is kind of abuse of notation. So I'm already thinking about the module. So this should be endomorphism valued power series, fractional power series of the module itself, not the B itself. This will be span. So now, Z plus half of plus 1 BR. But we still require this BR to be the generator of Heisenberg. Maybe it's better to put sigma. So this B is now the endomorphism of the module, not the original vector space. Is it too fast? Is that okay? At the end of the, if you want, you can just think of this as fractional power series, and then you can actually still construct the Virasoro. Yeah. -1? You're talking about first this? Yeah. Let me check. Is sum over IL? Yes, I think so.
I take like B minus 2 then?
B minus 2 is invariant, I think.
B minus 2 is like the derivative of the.
B minus 2 is the derivative of the first field. Yeah, I think that's right. Wait, that should not be what?
Maybe. The field associated with B minus 2.
Yeah.
Vacuum is just the derivative of
I understand your question, and I can't come up with the answer right away. But this is, okay, this is cheating, I know, but this is a correct definition as far as I remember. And this is actually called Obi-Ford CFT. So if you take a derivative, you might have to do some sort of justification coming from this Obi-Ford structure. Yeah. -1 to the n. No, -1 to the n is more like fermion thing actually, but yeah, because okay, the point is you basically want to classify the level of L0. That's also what you. So the same, if it's the same eigenvalue in terms of L0, you want to keep it as the same thing. So that's basically what this is doing. All right, so now we can do the same game. So we have the explicit representation of this guy, the twisted free boson operator. But because, again, we know some more structure about VOA, you can wish. And then, in fact, it's possible to think about this strictly. So now this is not necessarily power series anymore, but as explicitly writing down, it's fractional power series. This one, so as I said, it's invariant under sigma. And as I said, if it's invariant, we want to keep it as power series. And it's also, there's some formula that you can write down the Virasoro operator. And now, where sigma ln of sigma is defined by almost the same form. And then plus, ooh, I think it's 16. The center charge is 1, so this is 1 over 16. Say that again? Yes, thank you. Okay, it could be technical. I feel like someone might be quite confused, but at least conceptually, we have some sort of so-called free boson operator that generates Heisenberg algebra, the same as this one. But now by this machinery, what you can do is that you allow this to be half power series. Okay? But because we know some internal structure to construct, so we know how to write this, to write down this conformal vector, you can also write down, at least there's a formula to write down these Virasoro operators in 2 different ways. And now what's important is, remember, this is more like a little bit of spoiler, but remember, when we think about the Virasoro constraints, normally we think of L-1 or higher. We think of only subalgebra. So let's think of, okay, now I'm going to keep this. Okay, if you're not familiar with VOA, at the end of the day, you can just take it for granted and just accept it for now as just the formula of the Virasoro operators.
What are these sigma?
This sigma of R is an endomorphism acting on the module of VOA. So previously this is an endomorphism acting on the vector of this original. So now I'm thinking of actually a module. So there's some sort of map from this V to whatever the vector space you want to think of. And this B sigma acts on your favorite. Sorry, what?
You're not defining it.
I'm not defining in some sense. Okay, this, of course, I mean, is endomorphism of some U, where the U is, you're thinking some sort of representation of it.
So what have you said? So they satisfy this commutator?
Yeah, it satisfies this commutator relation.
What, you'd have not given more information?
No, I haven't given any more information on that. But what's important is at least this is now fractional. It's a half integer. This is actually, okay, then I'm going to tell you the biggest difference between this and that. So far, it looks like I'm just doing some. It looks almost like I'm repeating the same computation. Yeah. Ah, yes, thank you. Sorry? Okay, then I'm going to tell you what is the, so yes, so it looks like I'm repeating exactly the same thing. You could think, but this is more like, okay, sure, if you want to think of it from a geometric perspective, that is one way of thinking. And in fact, it would be correct. But for now, I'm more like doing some just because there's no geometry behind in principle. Yeah, the operators are not the same, of course. Yes. Right. Yeah, so this is, of course, the different thing. But okay, that's true. So first of all, this is a different thing. So it doesn't have any constant term in this L, but it does have constant term here. Okay. Then remember the quadratic Airy structures that you had on the previous board. If I multiply, so this L satisfies this Virasoro constraint. Sorry, Virasoro commutator relation. Okay, let's stick to no matter if it has sigma or not. That one also, of course, satisfies Virasoro. This also satisfies Virasoro subalgebra because I'm looking at only the higher part. If I
then if you form the same expression of those, it will satisfy the same computation relation.
no, the operators are different. So this is different from that. I mean, no. Yeah, exactly. So they oh, sorry, I'm so sorry. Yeah, but yeah. So the indices, okay, maybe okay. I should probably use SNR because that's what I was doing on my lecture notes, but okay, yeah, to make it clear, yeah, thanks. Okay, if that was your confusion, yes, it's absolutely fair. Yeah, sorry, yeah. Good. Now I guess, okay, so now, okay, at least you see that they're different, but I'm going to tell you exactly where. One of the part is this one.
Oh, that should be down there. Yeah.
Okay, yeah, this n is that n. Good, okay. All right, so they satisfies this commutation relation. Suppose I multiply by h bar, and I have h bar and h bar. Okay, I just multiply h bar squared on the both hand side. Now, if you think about this operator, it means you just multiply h bar here, right? And so this term would be the d term of the quadratic super structures. Does that make sense? Yeah. Okay, and remember that the second condition of Airy structure is that h bar times some fijk times some operators in your super Airy structures. So this h bar is also important. And then h bar, it will be multiplied on this term. This will be the d term. So this fixes f11. Okay. And now the second difference is, and also this one, now you don't have the constant term. So these Virasoro operators, or this representation, does not have d term, or d term is 0. Now let's think about a term. I don't know where I can write. Okay, I'm not doing well in time. So now let's look at a term in particular. Look at L minus 1 of this one. So the sum has to be minus 1, right? So you can have something like, for example, like B0, B minus 1, and blah, 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 blah. And in Ranier's lectures, you probably had the case that if it's negative, you can write this as some, okay, my notation probably Tn, something like this. You can represent it this way, and then I think B0, he has Q square root of h bar, but I set this to be 0 just for brevity. You can write this Bn as h bar d. Okay, strictly speaking, h bar, I'm a little cheating, but anyway. So this will be just the differential operators, and then you can actually see that there will be no a term appearing from this one. Okay, there's no x squared term or no square of the coordinate thing. But L minus 1 sigma, you can have something like this term, be minus half plus. And then the negative modes, as we learned in Ranier's lecture, will be converted into the coordinates of the Airy structures. So this term will look like something like half t, okay, probably in that notation. Maybe it's not the best notation. So it's going to be like something like this, plus that. And if you look at your notes on the previous page, this is exactly the form of the a term. So this will be a term of super Airy structure. Okay, so this will be the d term. Okay, sorry, I'm jumping around like left and back, right? But the punchline is that although it looks like I'm repeating almost the same computations, what I found from this fractional power series computation is that I found a non-zero a term and non-zero d term in the Virasoro algebra. And then as I noted some time ago, like maybe 15 minutes ago, that if both a term and d terms are 0, because it's recursive, free energy is going to be trivial, all of them are 0. So if you find Airy structure from this and higher Virasoro operators, you find a trivial Airy structure partition function. But this one gives non-trivial one, because it has a term and d term, non-zero a term and non-zero d terms. And that's why the twisted module is important. Twisted module is basically a technique to get non-zero or non-trivial area structure from a trivial area structure. Okay, and then there's a whole bunch of notations and calculation behind, but we are not gonna dive into that because I have only 20 minutes left. But is that okay? At least the conceptual part. Some Virasoro, like the canonical Virasoro operator construction, you do a little bit of a change, like this, just a fractional power series, and this tiny change gives a big difference in terms of area structures. Wait, is it actually mine? Yeah. Mm-hmm. Yes, it's actually a number in this case. Yeah. Yes. Yeah. Yes, that's right.
That's not the case, because in that case, this computation.
No. Yeah. Exactly. I mean, the sum has to be n. Okay. I mean, this is the concrete example. For example, like from this, for example, the sum has to be n. So you can have this kind of combination, zn minus 1. Yeah.
This is fractional. It sounds like you were adding fraction products and ramification. If you didn't have ramification in TR with some zero, but it's a trivial. Now you're ramifying it, so you get something.
Yes, you can say in that way too. Yeah. So you can say that this functional structure exists on the above the ramification, sorry, at the ramification of the double cover. That's one way of thinking it, but yeah. Yeah. By the way, in exercise, I have another derivation of basically equivalent Virasoro from this one. So another way of cooking up this one, but not going through this computation, but completely different one. And that is also, I think, interesting thing to look at. Any other questions? Good. Hopefully. All right. So now I have only 20 minutes left anyway. So okay, maybe just let me give first a comment. All right, so anyway, some technical details going on, but the punchline is that, okay, suppose after, so remember like in Rani's lecture, we learned that this is homogeneous in degree. So we have to get the, to satisfy the first condition of super area structure with the first condition of the area structures, you have to take some conjugation to reduce the degree by 1, and you actually get the correct area structure. So after conjugation, of L's by, I think in this notation, by e to the, is that correct? I think e to the b minus, I think this is correct, but I'll correct it maybe in the exercise session. Some conjugation, that I think what you remember is, this is all important. After conjugating of all this Ln, which is minus 1 or greater, by b minus 3/2, because now the b sigma, strictly speaking. And you actually get the degree 1 term. Then this Ln forms area structure. this is basically running a short with 4 generality of higher rank and also many, many conjugation parameters. But for the simplest case possible, if it's rank 2, okay, strictly a little bit different because he's doing GL2 and I'm doing SL2, but equivalent to what Rani is doing for the simplest case, and this forms an area structure. And then this means that there exists a unique tau function, or sorry, unique partition function that is annihilated by unique Z of area structure such that after conjugation, maybe I should say Hn. After conjugation, so the Hn is after conjugation equals 0. So this is Hn is for each n. And there is a unique partition function or free energy if you take a log, annihilated by this two-bit guy. Then it turns out that this Z, okay, let me give the name. This, what is the KDV maybe? This turns out to be exactly the same as the tau function of the KDV hierarchy, which is, okay, so it turns out this is the tau function of the so-called tau functions of the KDV hierarchy. And another way of saying is this is a generating function of psi class intersection number. Is that maybe? And this admits another name for physicists. This is a generating function of invariance of some Liouville gravity, 2 comma something. Some sort of gravitational. This is also the generating function of some quantum gravity. And this relates to some 2D gravity in physics. It's area structure. Did I say super area structure? Yeah. Oh, did I say super? Okay, sorry, yeah. Area structure. Okay, so even though this is one of the simplest Virasoro operators you can think of from the twisted module, the outcome is already interesting. So now what we can do, or what we want to do, is we want to basically have repeat exactly the same procedure with fermions, which basically gives not only Virasoro operators, but super Virasoro operators. And then you can ask the question. Any questions so far? Is conceptual part fine? Hopefully, yeah.
Say the 2 different VOAs, one for the boson part, one for the fermion part.
Mm-hmm.
So you're essentially doing some bigger Z2 gradient name.
Yes.
So that this sort of central.
Yeah, that's you're doing 2 different VOAs, right?
Yeah.
That's all what you're doing. Yes. Yeah, but that's not only about it. So I said this is just free boson VOA at some point. You can actually do free fermion VOA without bosons. That's actually totally fine. But to make it super symmetric, you have to think about some sort of intertwining operator between fermion and boson. That's good. All right, so yeah, I know it's getting quite technical, but sorry about that. But if we have to go through this. So skipping again all the details, but I'm gonna give you some sort of, so recall this, the free boson operator. Free boson operator was, okay, let's say B. But this is a free boson. This is just power series of whose most satisfies Heisenberg. So it's going to be n plus 1. This is the definition of Vz, where this satisfies the. Okay, why I have okay, this was my definition of free boson operator. And now I want to have so-called free fermion operator. Because I have 10 minutes, I'm not going to talk about any detail. Just I'm going to stick to only conceptual part. So now R is in Z plus half, but I still have half. So this is still power series in Z. The labeling is half integer, but the power is also half integer. So at the end, it's going to be power series. This is a common notation. For some reason, we use the same, but with sub indices. And now we impose that instead of Heisenberg algebra that we have, we impose that this mode would satisfy the Clifford algebra. N, M, and terms. Really? Did I forget?
Yeah.
Oh. Yes, I should have had it. This is the correct Heisenberg algebra. Really? Yeah, I forgot the. You could, yeah, but I mean, you have to rescale by square root of something. Right? Is that okay? No, I don't think so. Yeah. Okay, I didn't realize that, but this, you have to have n here. I'm sorry, but I guess nobody has done any detailed computation yet, so I guess it's fine. Yeah. Ah, okay, that's a shame, but yeah. Anyway, so this, now instead of Heisenberg algebra, no. Okay, good. Yes, good question. So the bosonic case, you want this indices here. And actually without n, it's actually inconsistent because if it's like this, the left-hand side is anti-commutative, like skew symmetric in n and m, because it's commutator, but this one is symmetric, so it has to be wrong. So you have to have this one to make this anti-symmetric. And now this is symmetric because it's anti-commutator, so it has to be symmetric. And sorry about that. All right, so R. R times delta. All right, so then now from which you can construct L n of the bosons is exactly the same way, same as before. And then Ln fermion, which is even. Okay, this can be, I think if I remember well, I think it's 1/4. Ln S in Z plus half and okay, believe or not, because we know how to construct this one. And then there is a canonical dictionary to construct the conformal vector for fermions, which will be the product of two fermions. So it's going to be even operators. So it's like the product of two fermions. It's an even operators, but so just it could be misleading, but it's fermion as in composed by fermions. All right, so in principle, you can do only this VOA without thinking about boson and vice versa. And this sometimes called VOSA, vertex operator superalgebra, but it's not supersymmetric algebra. When people say supersymmetric algebra, as we kind of saw, we want to have the G operator that we saw yesterday. So to talk about, in order to talk about supersymmetry, not doing just independently, now we want to, so from which we construct N of the total is just Ln boson plus Ln fermion. Okay, then because this and that commute with each other, the total one still satisfies the Virasoro commutation relation. Okay, they're completely independent. Okay, but now I further require the existence of such this kind of operator is just S and maybe K. No, I is better. Of normal ordering of okay, in addition to these Virasoro operators, so to say that they form a VOA, these Virasoro operators must exist. That's a part of the definition of VOA. But to say it's a supersymmetric VOA, you have to impose the existence of another operator, the GR that appeared in my last lecture, and then impose that they satisfies the super Virasoro commutation relation. And in this case, because everything is specific, by using this and that commutator and anti-commutator relation, you can actually show that these two generate the super Virasoro algebra in the so-called NS sector. Yeah. Three half. Yeah.
One half per fermion and one.
From boson. Yeah, only one fermion. I mean, it's a product of fermion, but that doesn't mean you have two fermions. Yeah. Side bar? No. The same as no B bar. Yeah. Okay, but in the same story, so I'm not talking about the fractional power series at the moment. So, okay, you can actually construct super structure from this, and you actually find out that the partition function of super structure is going to be trivial in exactly the same case as without super, right? So then now what you have to do is you have to think about the twisted module, allowing both boson and fermion to be a fractional power series, okay, without changing this commutation relation. You can still construct both G and L operators, and then now you find that non-trivial A term and D term appears in exactly the same way as this, the KdV type. Okay. And then, so now it looks like this is a very natural supersymmetric generalization of, for example, this KdV type area structure. So in terms of VOA and in terms of super Virasoro algebra, this is a natural supersymmetric generalization of the topological recursion you can think of. And now you can ask the question, so I drew some cartoon yesterday that, so we started, because I have to summarize, sorry, I'm rushing a lot now. But this is basically all I want to say. So just to recap, topological recursion is based on, so you have spectral curve, and this gives omega gn. They generate many interesting invariants in algebraic geometry. And there's a dual picture in terms of Virasoro constraint. In particular, it should be twisted module. Otherwise, there's no, as Raphael pointed out, otherwise you can't see those ramifying structure. So ramification on this side of order R corresponds to the rank of some W algebra on the algebraic side. If its R is 2, it's going to be Virasoro. So somehow this, or in particular, this super structure has this FGN. Right? If you expand the free energy of the area structure, you have this FGN. And what Ranier showed yesterday is that there's a dictionary, one-to-one corresponding dictionary between this GN and omega GN in the name of the Xi basis that he wrote down. All right, so what I did is, at least what we studied is we think about the supersymmetric generalization of this perspective. Now we have G of sigma acting on Z of superstructure, and this compute FGN for strictly speaking and greater than -1. Okay, and then as we saw, there exists a unique solution. So the existence is important because there is some non-trivial object here. And then this is partly work in progress with Ranier Nechler and Nicolas Rantan. So now, can we find a geometric description of the recursion we have from superstructure defined on a super Riemann surface? That's a natural question. Super topological recursion, can we do this? But now the super. Can we do this? It's partly written in my paper with Vincent, but now the full geometric description is still in progress. And I hope to report to you sometime soon. And I will stop here. Thank you. Yeah.
Is the eigenvalue model
Yes, but not directly. It's the same sense as, okay, this is a part of the exercise. Partition function matrix, okay, let's forget about super, because this already answers to your question. So, forget about super thing. Now you take untwisted Virasoro operators, and matrix model partition function is in fact annihilated by those. Okay, and it in fact gives global loop equations. Okay, this could be technical terminology, but every structure gives the local loop equations only at the ramification points. Okay, so they are essentially different. Of course, you can go from you can go from global loop equation to local loop equations. What do you mean? How do you match? You have to, okay. Yes, okay, you can show that there exists a super structure that solves super eigenvalue models, but you need 2 copies of super structures. The same thing as matrix models. You need 2 copies of Virasoro, local Virasoro, to get the global Virasoro. Exactly the same thing happening here. Well, at least 2, roughly speaking. Sorry, what? Yeah. Yeah, so you can write down loop equations, global loop equations from super eigenvalue models, and you expand at each ramification point, and you show that that loop equations at each ramification point is exactly the same as loop equation of super structures. That is done.
So what is the super?
This is in progress. It's a very good question. I mean, what is? Okay, so okay, this is important. So first of all, 1/1 super manifold is not necessarily super Riemann surface. So it has to admit some additional structure, so-called super conformal structure. Okay, so locally, basically, there must exist some sort of square root of d by dz. And that's basically one of the supersymmetry I wrote down yesterday about that the Q thing and D thing. If you take a square, it's going to be the derivative. So the Riemann surface should admit those, roughly speaking, the square root of canonical one, which is non-degenerate everywhere except few points. And those few points will be, in fact, exactly the ramification points. That's basically what I'm doing with Nechler and Rani. Good questions. We don't know at the moment, but we definitely have some expectations. So,
So do you expect it to be a connection valued in a super algebra or a connection valued in the algebra?
okay, at the moment, we don't know. We have some sort of speculation, but we can probably talk later. But it's a very good question, yeah. So one way of thinking is, okay, maybe this is working. I don't know if I should disclose it because it's recorded, but probably we should start with 3-half differential. If you think about, when you think about spectral curves. So the one way of thinking about spectral curves, you have quadratic differential with a map projection to normally P1. And then you can do many things. Okay, folks, the spectral curve of topological recursion is a little more data about omega 02, but roughly that's all you need. This one, I think we are almost convinced that we need 3-half differential to start with on a super Riemann surface with some super cover structure. And then we will write down the recursion in a few months, maybe. Yeah, with some corrections. But yeah, that's definitely a good question. We won't answer that. Any other question? Yeah.
So going back to the start, when you said the 3 of H-2, I think there's like papers of Castello and Afray, Colorado, and things where they define exploration variance, and in there I think it's natural that the degree of H-bar is like 2. The problem is I don't really know what any of those would mean.
Okay. No, because
Yeah, that was
okay, yeah, but yeah, I think it's yeah.
And then also, you ever run the expression about being able to be extended to like the infinite dimensional case? Is there any problems with?
Yes, good question. So if you extend the area structures, super structures to the infinite dimensional case, that's your question, right? And then when it may break down. Okay, so yes, I know some instances that breaks down. So basically, the proof goes like with the answers that order by, if you fix G and N, you have only finitely many terms. So in principle, the A term that I wrote down, if you have infinitely many, you can have infinitely many A terms, and that may cause the problem. That I remember, but other detail I can't remember. But like if you have finitely many A terms, the A term, because it's special, because it fixes some specific things, and then if as far as I remember, it's fine. Like this case. Yeah, you have only one A term. Yeah, right.
Different ways of getting around it. But you need some kind of financial solution locally.
Right.
So you're saying that if you have that it's not different.
Yeah. Yeah. Okay, that's actually question 5 in my exercise sheet. I have 4 questions, each of which consists of 4 more questions. But then if the question 5 is if you solve everything and just come talk to me, and I can talk about this. I've already thought about that n equal 2 and have some ideas, but I would probably need another hour to explain what's going on. So, yeah. Yeah.
Is there a relation between these partition functions and structures from the area structures and characters of the OA?
Characters, because it's going to be highest weight vector of the module. The characteristic, I'm not sure if I understand the question. Yeah.
Which numerical geometry applications do you expect? Like, do you expect something like super, I don't know, super Hermitian invariant stuff like this, or do you?
If you do Hermitian invariance or something with false cosmology, will need some geometry.
Yeah.
an expectation.
Yes. For example, if you do theory of elliptic curves.
Yes. Yeah. Yeah. Okay.
There are some
Mhm.
all parts are not exactly the one.
Yeah. Yeah. Sure. I know what paper you're talking about. Yes. So I'm not sure at the moment because our approach is basically purely algebraic point of view, like in terms of UA. That's a natural generalization of, but it's not the thing. And as I said at the beginning, the super really means it depends on who you talk to. But at least I would expect if there exists some sort of square root of psi classes, wherever it's defined over, and then that would be probably some sort of intersection numbers that we should think of. But this is just a naive guess.
Even if you go to a superunion surface, you still get integrals on MGN, right? So should it confuse the Riemann surfaces of the moduli space where we intersect and whatever is the input for the recursion, right?
No, but they're different things.
Yeah, exactly. One of them is not super, so I don't see why you would.
No, but I don't. No, I don't understand. Because I mean, some supersymmetric theory can be computed by topological recursion without super. That's completely fine. So
Taking square root of non-equals, you're integrating on moduli space that has more than these things.
Quite possibly we need to look at spin structures, but which I think spin structures is very close to it with topological recursion anyway, because that's basically with its spin classes. So it wouldn't be surprising.
I think I think also the x variables, some of them are now, these are index of class, usually they're index of all class. You would have orthogonal.
Yeah.
So does that mean you expect to be able to write a general solution for the super TR in the same way you would write it for TR?
What do you mean by general solution? Solution of what? No, oh yeah, the super dot is somewhat we wanna do. Yeah, right. The super dot is kind of the goal of our project. Okay, I guess even I'm a speaker, I guess I have to stop this and then maybe. And then I know we have many questions, but we have more discussion time. Yeah. I don't know.
It should be analyzed by potential. That would be a
Well, because super orthogonal polynomial, what do you mean? Do you start with super matrix models? Is that what you have in mind? I mean, the matrix itself will be super, but I'm not sure if it's going to have nice structure because the fermionic integral really messes things up, and you have to be really careful about some formula. And in particular, as I kind of noted, like so to define matrix model, you have to really, really be careful what you mean by the partition function. And then as far as I know, if it's one cut case, I know how to define it. If it's not one cut, I'm like not sure how I can rigorously define matrix models. Maybe it's possible, and I think it's possible, but I don't know at the moment. So yeah, I guess. Yeah, I think so. Yeah. No, super quantum candidates, we already have some. I mean, that's because we have loop equations, so you can, of course, cook something up.
hard to go from equations to
I don't know. I don't. At least Bosonic case, if I have global loop equations, I think for rank 2, I'm pretty confident I can construct at least perturbative quantum curve. So, yeah. 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 Thank you.